Imagine you are sitting inside a military radar station. The room is dim. Several operators are watching glowing green radar screens. Outside, a massive radar antenna is slowly rotating. Every few seconds, that radar sends out thousands of radio waves into the sky. Those waves travel hundreds of kilometers in every direction. Anything flying above the horizon should show up on the radar screen. Passenger planes show up, cargo aircraft show up, birds sometimes show up, even large storm clouds can show up. So radar operators usually have a pretty clear picture of what is happening in the sky around them. But then something strange happens. A fighter jet flies straight through the radar coverage area. It is not far away, it is moving quickly, and it should be very easy to detect. But the radar screen shows absolutely nothing. No signal, no warning, no aircraft. To the radar operator, the sky looks completely empty, but it isn't, because a fighter jet just flew directly through the radar network, and the radar barely noticed. This is the basic idea behind stealth aircraft. But here's the interesting part. Stealth aircraft are not actually invisible. Radar waves still hit them. They still reflect energy. So the real question becomes this: how can an aircraft still reflect radar signals and yet remain almost impossible to detect? To answer that question, we need to understand how radar works. And the answer turns out to be a fascinating mix of physics, mathematics, and Cold War engineering. But before we get into the physics, there is a strange historical twist. Because the idea that eventually led to stealth aircraft didn't come from an aircraft engineer, and it didn't come from a fighter pilot either. Instead, it came from a mathematician studying how radar waves bounce off objects. His calculations were so unusual that for a long time, nobody believed they could actually work in real life. But eventually, those ideas led to one of the most secretive aircraft programs ever created. We'll come back to that story in a moment. First, we need to understand something simple: how radar actually sees the sky. Stealth aircraft are just one example of the hidden technologies shaping the modern world. From secret military strategies, to powerful scientific discoveries, to global systems that quietly influence everyday life, Curiosphere explores the fascinating questions that shape our world behind the scenes. So if you enjoy discovering how the world really works, consider subscribing and stepping deeper into the sphere of curiosity. Now let's start with the basics: how radar actually works. Radar works using a very simple idea. It is basically the same concept as an echo. If you shout into a canyon, the sound waves travel outward, hit the canyon wall, and bounce back toward you. Radar works almost exactly the same way. Instead of sound waves, radar sends out radio waves. And instead of canyon walls, those waves bounce off objects in the sky. The radar antenna sends out a pulse of radio energy. That pulse travels outward at the speed of light. When it hits an aircraft, some of the energy reflects back toward the radar. By measuring how long it takes for the signal to return, the radar can determine distance. By measuring how the signal shifts, the radar can estimate speed and direction. This technology changed warfare completely during World War II. Before radar, aircraft could approach cities or fleets almost unnoticed. Bombers could appear suddenly over their targets. Naval ships could be attacked with very little warning, but radar changed that. Suddenly, aircraft could be detected hundreds of kilometers away. Air defenses could prepare. Fighter aircraft could scramble. Missile systems could activate. Radar removed one of the most powerful advantages in warfare: surprise. But that also created a new challenge. If radar could detect almost every aircraft, then defeating radar became one of the biggest technological goals of the Cold War. Engineers tried several ideas: flying faster, flying lower, using electronic jamming, but none of those methods truly solved the problem. Because aircraft are large metal machines, and metal reflects radar waves extremely well. Even a small fighter jet can appear clearly on radar, unless something changes the way radar waves interact with the aircraft itself, and that discovery would eventually change aircraft design forever. To understand stealth aircraft, we need to understand how radar reflections work. Imagine shining a flashlight at a mirror. The light reflects directly back toward you, but now imagine shining that flashlight at a tilted piece of glass. Instead of reflecting back toward you, the light deflects off in another direction. Radar waves behave in almost exactly the same way. If radar waves hit a flat surface facing the radar antenna, they reflect strongly back. But if the surface is angled, the waves scatter away, which means much less energy returns to the radar receiver. During the Cold War, scientists began studying how radar waves scatter when they hit different shapes. Computer simulations were used to model thousands of different surfaces, and the results were surprising. Smooth, curved aircraft reflected radar signals very strongly, but sharp-angled surfaces scattered radar energy away from the radar source. The designs looked strange. Very strange. Aircraft that looked almost like flying crystals. But mathematically, they worked. One of the first aircraft built using this idea was the F-117 Nighthawk stealth attack aircraft. When the aircraft was finally revealed publicly in the late 1980s, it shocked aviation experts because it looked nothing like a normal airplane. Sharp edges, flat panels, angular surfaces everywhere. But those strange shapes were not accidental. Every surface was designed to scatter radar waves away from radar receivers. But shaping the aircraft was only part of the solution. Even with carefully angled surfaces, radar waves still bounce off metal, so engineers developed another idea: special coatings designed to absorb radar energy. These coatings are called radar-absorbing materials. At a microscopic level, these materials interact with radar waves and convert that energy into tiny amounts of heat, which means less energy returns to the radar antenna. A good analogy is soundproof foam. In recording studios, foam absorbs sound waves so they don't bounce around the room. Radar-absorbing materials perform a similar function for radio waves, but building these materials is extremely difficult. They must survive extreme temperatures. Supersonic airflow, heavy rain, dust, and pressure changes at high altitude. Even small scratches can increase radar visibility, which is why stealth aircraft require extremely careful maintenance. Aircraft like the F-35 Lightning II stealth fighter undergo constant surface inspections after flights. Radar is not the only way aircraft can be detected. Jet engines produce enormous heat. Inside a fighter jet engine, temperatures can exceed 1,500 degrees Celsius. This heat produces infrared radiation. Infrared sensors can detect that heat from long distances, which means even if an aircraft avoids radar detection, it could still be detected by heat-seeking sensors. So engineers had to reduce infrared signatures as well. One solution is to hide the engines deep inside the aircraft body. Another solution is to mix hot exhaust gases with cooler air before they leave the aircraft. Some aircraft spread the exhaust across wide surfaces to disperse heat. A good example is the B-2 Spirit stealth bomber. Its engines are buried deep inside the wing structure, reducing both radar and infrared visibility. Stealth aircraft are not truly invisible. Instead, they become extremely difficult to detect. Think of it like dimming a light. The light still exists, but it becomes much harder to see. Some radar systems can sometimes detect stealth aircraft under certain conditions. Low-frequency radar may detect larger stealth aircraft, but these systems usually lack the precision needed to guide weapons. This creates a strange situation. An enemy radar might suspect something is present, but cannot track it accurately. That uncertainty gives stealth aircraft a major advantage. Aircraft like the F-22 Raptor stealth fighter can enter defended airspace before enemy defenses fully react. Building stealth aircraft is incredibly difficult. It requires expertise in aerodynamics, radar physics, material science, computer modeling, and extremely precise manufacturing. All of these technologies must work together perfectly. Even small design mistakes can dramatically increase radar visibility. That is why only a few countries have successfully developed advanced stealth aircraft. The engineering complexity creates a huge technological barrier, and that barrier provides a powerful strategic advantage. Because in modern warfare, the aircraft that cannot be detected is often the aircraft that cannot be stopped. Stealth aircraft are not magic. They do not truly disappear. Instead, they represent one of the most impressive combinations of physics and engineering ever developed. By shaping aircraft surfaces, absorbing radar energy, and controlling heat signatures, engineers created machines capable of slipping through some of the most advanced detection systems ever built. And in the strategic chess game of global military power, sometimes the most powerful aircraft in the sky is the one you never see.